Okay, welcome everyone to another Utrecht Philosophy of Astronomy and Cosmology Colloquium. Today we have our speaker session. Jonas is talking here today about black holes. He has a background in physics, did a PhD at Amsterdam University, also postdoctoral research in Germany, and now mostly I think science writer and communicator. And he's working on a book on black holes. And today his talk is based on a chapter of it.
Okay, good. So let's get started with this seminar. And the topic is the universe a black hole? So why did I choose this topic? It's because during the pandemic, I guess many of you, at least like me, spent a lot of time on YouTube doing nothing really. And if you do that, you might come across these kind of YouTube videos where some very prominent physicists discuss the question of if the universe is a black hole. And if you also look in the science literature, you also see these kind of statements floating around. Here is Susskind, for example, far out at about 15 billion light years, our cosmic horizon is swarming galaxies, stars, and probably even life. It is as if we all live in our own private inside-out black hole. The answer to the question, is the universe itself a big black hole, is a qualified yes, says Melia. And then in this note, we consider the properties of a daughter universe spawned from the interior of a black hole resting in a mother universe. So both in terms of popular science, but also in the scientific literature, this statement is floating around that the universe could be a black hole. So for my popular science book about black holes, of course, when I see this kind of statement, I get very curious. What lies behind this? What's the actual physics? Is there something more going on here than just a fluffy statement? So the goal of this talk is to kind of survey the literature a bit and see what the arguments are about this, and then also have a discussion about this. So, but to continue with the motivation, why are people making these claims in the first place? And you can see that if you take a look at a plot of, this was a very recent paper just a few weeks ago, where they looked at different objects in the universe, mapping out their radius and mass. And just seeing, like, making a map of what we have in the universe. So for example, if you take the Earth, it's down here somewhere. So here is this is measured in solar masses. So of course the sun should have 1 solar mass. So it's a log plot. So 0 corresponds to 1 solar mass. We can also look at the Milky Way. It has a bigger radius, larger mass. Same with superclusters in the universe, some of the biggest coherent objects in the universe. And then we can draw a line on this plot that corresponds to if we have an object that satisfies this Schwarzschild relationship. So you take a mass, given mass, and you compute the Schwarzschild radius. So this is the one that's very famously for the Earth. It's just about 8 millimeters. For the sun, it's 3 kilometers. So most objects in the universe have a radius that is larger than the Schwarzschild radius. But then, of course, black holes would lie on this line. Stellar mass black holes, supermassive black holes, and then, of course, the universe. So we can take the mass of everything in the universe that we can see and compute the Schwarzschild radius of that mass. Oh, sorry, we can take the mass in the universe and we can look at the observable universe, how big that is, and then it ends up here. So this is the motivation that made people start to think about if the universe could be a black hole. So much of this talk is actually about trying to understand why this is like this and what kind of consequences we can draw from that. So let's look at some more equations here, because now we've been talking about mass and radius, but the universe is mostly empty. It has a very low density, but you can actually compute something that is like a Schwarzschild density. So you take the density of an object, so that's just the mass divided by the volume. So if you take the volume, be defined by the Schwarzschild radius, just like a sphere, and you plug in the Schwarzschild radius here, you get this relationship. And the interesting point about this is that the mass appears here in the denominator to the power of 2. So this means that the larger mass you have, the smaller or lesser density you have. So for example, for these supermassive black holes, they actually have a very, very low density. It's on the order of our atmosphere, or even lower than that. So you don't really have to have extreme physics going on to form a black hole. You can have very low densities. And in particular for the universe, it only has a few atoms per cubic meters, something on the order of that. And then if you take the mass of the universe, that's often quoted as 10 to the power 54 kilograms. You take the radius of the observable universe, and I'm going to go back to where this number comes to in the future of this talk. So this is the radius of the observable universe. Now we take the mass of the universe, plug it into this formula, and then we get the Schwarzschild radius. It's actually about 3 times larger than the observable universe. It's quite intriguing. So what does it mean? So the goal of this talk is to see then, is our universe a black hole? Based on that kind of back of the envelope calculation. Could it also be that black holes actually create new universes? And if so, could it be that our universe came from a black hole? So we're going to investigate that. And the starting point here is our universe a black hole. What we have to do is to compare what we know about the universe and compare that to what we know about black holes and see if we can find some similarities beyond this Schwarzschild radius computation. But that poses a question because when are 2 objects the same? So for example, if I have a hurricane here, and then I take a galaxy, I see that both of these objects have these kind of beautiful spiral structures. They have some kind of thing going on at the center. And in some cases, we can use similar equations also to describe them, using hydrodynamics, Newtonian force law, and so on. So there are similarities. But of course, nobody would really claim that just because we have similar features, they're actually the same kind of object. And that's the question we have to ask also when we want to see if the universe is like a black hole. Just because they have some shared features, are they the same object? And the shared features that we are going to zoom in on are the presence of horizons and the presence of singularities, because both occur for the universe and for a black hole. So we have to see how the horizon looks for a black hole, compare that to the universe. We have to see how the singularity looks for a black hole, compare that to the universe, and then see if we can establish an identity. So let's start by just diving into a black hole and see what goes on there. If we are in the inside of a black hole, surely we must see what is actually the inside of a black hole. So this is an animation by Enander, a Parisian astrophysicist, who has done very realistic animations of what happens when you enter a black hole. In this case, it's a Schwarzschild black hole that only has a mass, no rotation, no electric charge. And the first thing we would see is this very interesting gravitational lensing effect on the outside. But at some point, we will actually fall into the black hole and pass the event horizon. But the crucial point there is that nothing really happens as we pass the event horizon. There's nothing special there. There's no sign saying, now we passed it, because there we actually passed the event horizon. You can see that from the velocity here. What happens on the inside is that we can see all the light from the exterior universe getting focused into this ring surrounding us. And because of the high Doppler effects in our back and lensing effects, everything from the exterior universe seems to get squeezed into this ring of light. And it kind of looks now as we approach the singularity as we're landing on the surface of a dark planet with a dark sky above us. So this is what you would see if you fell into a black hole. Of course, you would be dead already by now. So I don't recommend it. So we can use a much more safe way to study black holes. And that is Penrose diagrams. They are great. Because if we want to look at what a horizon is, we really have to look at the causal structure of space-time. And if we want to look at the causal structure of space-time, we have to know what happens far away in infinity, both in spatial infinity, but also in terms of time, the infinite past and the infinite future. So somehow we have to represent these infinities on a finite region. And this is how it's done on a space-time diagram. So space goes in this direction along this axis, and time goes up. The point with these diagrams is that light always travels at 45-degree angles. So a light ray starting all the way from the infinite past would go down here and go to the future. So this is the infinite past for all light rays, and it passes different radii described by these curves as it travels to the infinite future. And time are given by these kind of slices. This is a constant time slice. And these are some other ones. So as the light ray passes through different radii, it also passes through different points in time. But material particles that don't travel at the speed of light, they instead start from the infinite past, which is a point down here, and then up in the infinite future, which is a point up here. So this is a way of representing infinities on this kind of conformal diagrams. In this case, this green line would correspond to a particle that's more or less sitting at the same radius and just hanging out there from the infinite past to the infinite future. The reason that I choose that kind of trajectory was that in Keynote I couldn't make it go around and animate it that same. But that's okay. This would be something like a Minkowski space, a flat space time. But now we can also look at the causal structure of a Schwarzschild black hole. Why do we choose them? They are the easiest black holes that we can choose. Only mass, no rotation, no electric charge. And if we want to compare the universe to a black hole, we should start with the simplest case and see if we can touch base there. So this is the causal structure of a Schwarzschild black hole. It's a bit more complicated. The most important thing in this diagram are these lines. These are the horizons of a black hole. Notice that they are defined by these trajectories of light, and then what's called a null surface. So they aren't like the surface of the Earth, which is defined by these kind of material particles traveling at below the speed of light. Instead, the horizon of a black hole is actually defined by these kind of light trajectories. And light can still, and the radius of this horizon is still given by the Schwarzschild formula. Lights can still travel far away from the black hole, enter the horizon, and then at some point hit the singularity inside the black hole. But notice that you can't send a light ray outside the horizon because light rays travel at these 45-degree angles, and nothing can travel at a higher angle than that. That would correspond to superluminal velocities. So that's the reason why you can't really go outside the horizon, is that you can't send any light rays in the opposite direction. So once you have entered the horizon, you're stuck there. There are no trajectories that go out of it. And at some point in time, it doesn't have to be the infinite past. You can also drop a stone into the black hole from here. It will pass the horizon, and at some point it has to hit the singularity here. And once it has passed the horizon, there's no trajectory that the stone can take that leaves out of it, because it can't travel faster than the speed of light. But there's also some other peculiarity. In this plot, we also have light rays that can start here and go out of this horizon down here. That corresponds to a white hole. And there are also light rays that can start from the infinite past here and pass this part of the horizon and actually interact with stone that we, or astronaut or whatever, inside the horizon. And this corresponds to another universe that's causally disconnected from this region, but they can interact within the black hole. Now, this is the most general mathematical formulation of a Schwarzschild black hole. This doesn't mean that nature actually behaves like this. If you have gravitational collapse of astrophysical objects creating black holes, they would not create this kind of global structure. They would not create this kind of other black hole or white or other universe or a white hole. But for the universe, if we want to create that with a black hole, we have to start with the most general thing we think of, and then see what happens there, and if that corresponds to something that we observe in the universe. So, what about horizons in a cosmological setting? This was formulated by Rindler in 1956. A great paper called Visual Horizons in World Models. And it was really during the 50s that our understanding of the horizon structure, both in cosmology and for black holes, started to take shape. And in cosmology, there are two horizons, not only one, two types of horizons. Rindler writes, and this is the definition still used: we shall define a horizon as a frontier between things observable and things unobservable. The vague term things is here used deliberately. There are then two quite different horizon concepts in cosmology, which satisfy our definition and to which cosmologists have at various times devoted their attention. The first, which I should call an event horizon. So here now your brain is like, wow, event horizon, I recognize it. It's exemplified by the de Sitter of the universe. It may be defined as follows. An event horizon for a given fundamental observer A is a hypersurface in space-time which divides all events into two non-empty classes: those that have been, are, or will be observable by A, and those that are forever outside A's possible power of observation. What does this mean? It means that we are here now, and we have the entire universe around us. So how far away can we see, given that we could wait an infinite time for light signals to come from other objects in the universe? Can we see infinitely far if we wait an infinite time? Or is there a limit to how far away we could see because of the expansion of the universe? So that's the event horizon. It concerns what we could potentially see in an infinite time. Then we have the other definition. The other type of horizon, which I should call a particle horizon, is exemplified by Einstein's de Sitter model universe. It may be defined as follows: a particle horizon for any given fundamental observer A and cosmic instant t, 0, is a surface in the instantaneous 3 space t equals t0, which divides all fundamental particles into two non-empty classes: those that have already been observable by A at the time t0, and those that have not. Okay, what does this mean? Again, we are here now, so we call our time now t0. The question now is, how far back in the past can we see? Because it takes time for light to travel to us. So is there a limit to how far we can see in the past? For example, if we look at this kind of image, the double deep field, here we see galaxies at different stages in the past of the universe. How far away are they? Why can't we see even further away? Why is there a limit to how far back in time we can see? That's the particle horizon. The event horizon will tell us, okay, we have this in galaxies. So let's now stand and stare at them for 1 million years, 1 billion years, for an infinite time. They will, of course, evolve, just like the things on Earth evolve. They will also be redshifted, and at one point, the light of them will be maybe infinitely redshifted, and we won't see them. So they will leave our horizon, our event horizon. Okay, so how do we describe this? Well, we use the Friedmann equation. That's a fundamental equation we use to describe horizons and the expansion of the universe and potential contraction of the universe. Does anyone remember what this quote is from? 2 years ago, roughly. This was from demonstrations in China against the pandemic restrictions, and they hold up signs saying the Friedman, free man. So it was, yeah, a bit bizarre. Okay, so with the Friedmann equation, we can describe the expansion of the universe, and that depends on the matter and energy content of the universe. And we have different eras. We have these kind of eras: radiation dominated. The scale factor, which describes the expansion history, went like a power law. Matter domination, we have also a power law, dependence on time for the scale factor, a bit higher. And then in the future, we have dark energy domination. And if we describe that by cosmological constant, the easiest solution, then it will actually have an exponential expansion. And that's what's causing our trouble in terms of horizons. So, trouble, depending on what you want to call it. So what do we actually have about the horizon structure of our universe? Well, it kind of looks like this. This is a fantastic plot. It's from a paper 2004 by Davis and Ingweaver. And it may look a bit messy, but this contains really the state of our knowledge about the causes structure of the universe. So We're going to spend some time on it. Let's first look at the co-moving, or the x-axis. It describes co-moving distance. So that's not the physical distance to other galaxies in the universe. That's a label we put to that. So if Niels is another galaxy and I'm sitting in the center, and Niels is expanding away from me, the physical distance will decrease. Like I still put a label on Niels and saying that, well, today the distance is 2 meters. Maybe tomorrow the distance is 4 meters, but I still put the label 2 meters because that's what it was today. So just keep that co-moving distance to other galaxies in the universe. So the co-moving distance is the distance we have to different galaxies today. Then here I have something called conformal time. That's just a way of rescaling the time axis to make all light trajectories in this diagram move at these 45-degree angles. This is a better axis to look at. This is the scale factor, and it changes with time. So it goes from 0.001, that's roughly the time when the CMB was emitted. It's 1 today, and it will go to 1, and then 2, and 3, and then to infinity. So this is kind of like a conformal diagram in that we do this kind of conformal rescaling, so I can actually see what happens in the infinite future. So first of all, what are other galaxies doing? Well, they are sitting at a fixed point. First of all, we are sitting here in the middle, here. We're in the center of the coordinate system, happy, not moving around at all. Then we have other galaxies. They are sitting at fixed co-moving distance. So here's one that would be somewhere between redshift 1 and 3 when we observe it. So all this would be different galaxies at different redshifts or different objects emitting light at different redshifts. And what we can do is, for example, at some point in time, this galaxy here is emitting a light ray from there, a 45-degree angle. And we see it at that point. At some other point in time goes up, it also emits a light ray. And we see it today. So this is the image we will see of the galaxy today that hits us at Baptisium today. Now. So we can start to see what happens with these light rays at different points in time. For example, we could ask, what is the furthest distance that light could have traveled from in the infinite past? That would correspond to the particle horizon. So we trace this light cone, our past light cone, all the way to the beginning. And that's our particle horizon, because all galaxies out to this distance could have sent light rays to us today. So if I go up from this point, I see that here's the particle horizon intersecting our now at this point. That's roughly 46.5 billion light years. So that's what we saw when I said the observable universe. It corresponds to 46.5 billion light years. So we can see light coming from galaxies that was emitted a long time ago, and now they are at a distance of 46.5 billion light years. Of course, we can't see them now because they are that far away. We have to wait in the future and see if we can see them then. So what you see is that the particle horizon is increasing in time. But then we also have an event horizon, because this galaxy here, we see it now, it's on our past light cone. We can emit some light at a later point, and we can see it here in the future, how it evolves. But at some point, it will emit light all the way to infinity, and we are here, but we can't see it. So it will actually exit this event horizon, and we can no longer see the light emitted by this galaxy, even if we wait an infinite time. And that defines this event horizon. The event horizon is our past light cone at infinity. So that means that all this gray area here is a part of the universe whose light can never reach us. So that kind of reminds us a bit of a black hole, in the sense that there is a region of space-time which we are causally disconnected. And in the same way, there is a region of the universe that we are right now causally disconnected from. But there's also this Hubble sphere, and the Hubble sphere defines a surface around us where things are receding right now at the speed of light. And that's often a source of confusion, because if they're going away from us at the speed of light and emitting light, how can we see that light? They can do that because that light ray initially will move away from us, but at some point in a matter-dominated universe, the expansion will slow down a bit. And it will enter a region where it can overtake the expansion and finally reach us. So all this blue area is part of the universe where light is emitted at a region that is expanding faster than the speed of light away from us, or we can still see it. So this galaxy, for example, actually enters the Hubble sphere and then leaves it again. But around this time here, dark energy starts to take over, and it changes the Hubble sphere, the shape of the Hubble sphere. And actually makes it coincide with the event horizon in the future. What happens is that all galaxies will, no matter how close they are from us, they will exit the event horizon, and we will not see the light from them in the future. So anything that's not gravitationally bound to us, like the local Andromeda galaxy or whatever, will leave the event horizon and become causally disconnected. So this is what we would call an event horizon. Now, what about this relationship that we talked about of Schwarzschild? It turns out it's a very, very trivial computation, but it's rarely mentioned. Sean Carroll mentions it in a blog post, but otherwise I haven't seen it. It's very trivial to calculate that in a flat universe, this relationship holds on the Hubble sphere. So the radius of the Hubble sphere in a flat universe will always satisfy this relationship. So the mass enclosed here in this dark region, all that mass lies within the Hubble sphere. So it's exactly the Schwarzschild relationship. It means that any other radius that where we evaluate if this Schwarzschild relationship holds or not, that is larger than the Hubble sphere, we will always see that the mass is contained within this Schwarzschild radius. So that's what we saw in the calculation in the beginning. The Schwarzschild radius is about 3 times larger than the observable radius. The Schwarzschild radius here's the observable universe. It's this point where the particle horizon is, and then the Schwarzschild radius would be somewhere outside here. You can show that always has to hold if you have a constant energy density. But it's important to remember that the Hubble sphere is not a horizon. There's nothing special about it. It signals that you have expansion at the speed of light there, but we can still get signals from outside the Hubble sphere. So it's not a horizon. So what can we conclude from this in terms of the horizon? Well, one important point to mention also is that this causality structure is defined with respect to us. But if someone else is sitting here and also believing that they are in the center of the universe, they will also have a causal structure that looks similar, but at that point. So there are some differences with a black hole. So let's see. Anyone inside a black hole can get signals from outside the horizon. So if we are inside a black hole, we can get signals from outside the horizon. No one inside the cosmic event horizon can get signals from outside the horizon. So they're like in an inverse relationship to each other. The cosmic event horizon is relative to the observer. The Schwarzschild event horizon is an absolute non-surface. So one type of horizon is relative, the other one is an absolute surface in space-time. And in a flat universe, the Hubble sphere will always have a radius given by 2gm over c squared, where m is the mass enclosed within the Hubble sphere. But this does not necessarily mean something is or will become a black hole. This is called a Hooke conjecture from Kip Thorne in the 70s. And just because you have a radius and you put a mass inside of there, and that radius would correspond to the Schwarzschild radius, does not mean, it's not known what the general condition is for this to form a black hole. But it's, for example, I highly believe that you need some kind of contraction going on, some initial contraction, so it starts to collapse. So this is not proven for generality yet. So just because you have this Schwarzschild relationship holding for the universe, that does not mean that it is or will become a black hole. So I think if you look at this kind of basic arguments, it becomes a bit shaky that the universe would be a black hole. But what about the singularity? Because we have a singularity in a black hole, we might or might not have a singularity in the past of the universe. So let's have a look at that. So again, going back to this plot, we have the event horizons. Those are absolute hypersurfaces in space-time. Then we have the singularity up here. The singularity inside a short black hole is not a point in space. It's not a point in the center of the black hole. It's not a point that you can kind of go to, have a look at, and then go away from there and write a message to someone else who's also inside the black hole and tell you what you saw. The singularity inside the black hole is a point in time that lies in the future. And it fills the entire black hole at that point in time. That's why you can't escape it. So if you have a light ray going into the black hole, it will pass the event horizon and always go forward in time, and at some point it will reach the singularity. You can send a light ray at a later point in time from the outside. It will also hit the singularity, but at another spatial point inside the black hole. But it's still the same time inside the black hole. That's the fascinating thing. You can send it again, another one at a later time. Notice also that no light rays can come in the opposite direction. Light always travels at these 45 degrees angles upwards in these conformal diagrams. That means that you can't really see the singularity. You don't see anything from it before you hit it. Just like you can't see the future before you reach the future. Okay? So the singularity inside a black hole is a bit counterintuitive. So let's look at it even more. So this is usually how we picture the mathematical description of the exterior of a black hole, is that we set up some kind of grid lines outside of it. And that's what we use, these Schwarzschild coordinates. They correspond to radial parts and times outside the black hole. But as is well known, but which also caused a lot of confusion for several decades, is that this coordinate system becomes singular at the horizon. That's a coordinate singularity. So you can transform into other coordinates, pass the horizon with those coordinates, and see what happens on the inner side with those coordinates. So that's a solved problem in the 50s. But you can still use this metric, this equation, on the inside of a black hole. But you have to remember that what we here call the time coordinate and the radial coordinate, they switch roles on the interior. So we do a transformation just to make that explicit. And I have a little minus sign just because of the way time, if I want time to increase corresponding to proper time increasing, I have a minus sign. And then I write it like this. So here's my time coordinate t, here's my radial coordinate r inside of the black hole. But this looks very, very funky because now I have a time piece in my metric. I have a time piece here sitting in front of my angular part of the metric. That means that the interior of a black hole is not static, it changes with time. So this is actually a kind of a cosmological solution inside of the black hole. So if we zoom in at that and actually take a look at what it looks like, and this has been well studied, here's just one reference as an example. There are a lot of kind of counterintuitive things that happens. One is that the interior volume actually increases with time. From the outside, it looks fixed, but on the inside, it actually increases. It's a bit like Alice in Wonderland. You know, it's a very counterintuitive world that we enter. This has also been well studied. That fact actually makes it very hard to make the statement where you say that, well, the energy density of a black hole, I just take its mass, I divide by the volume. What volume? Because that changes with time. So we have to be very, very careful here. The time to reach the singularity is proportional to the black hole mass. So if it's a stellar mass black hole, it's just a few nano-microseconds, something like that. If it's a supermassive black hole, it's on the order of minutes, or even days. You can actually spend some time in there. You can even pass the horizon safely. But near the singularity, the space-time can be approximated by the homogeneous but anisotropic Haskell metric. This is a cosmological solution that was published, I think, 21, very, very early. What that entails is that space expands in one direction, but contracts in the other direction. That's like a full-blown space-time description of this thing that we talk about the tidal forces as you fall towards black hole, where you get spaghettified. So you get, if you fall with your feet first, you get stretched out in the direction the way you're falling and squeezed out on the sides. Inside the black hole, this is actually an entire cosmological description of that. So you have expansion in one direction, but you have contraction in two other directions. That doesn't sound like our universe. In our universe, you have expansion in all directions. It's an isotropic expansion. But in a black hole, it's a Blackwell solution where two directions are contracting and one is expanding. It even becomes infinite the radial direction. There are other things, too, worth mentioning. How do we actually know there is a singularity at this r equals 0, which is a time coordinate inside a black hole? We use this thing called the Kretschmann curvature scalar. So we need a coordinate invariant way of describing divergences inside the black hole. We form this by squaring the Riemann tensor, which is our fundamental geometrical object of spacetime. And this Riemann tensor, it can be decomposed in full. This is fully general before we even start talking about black holes or whatever. It can be decomposed in two parts. One is called the wave tensor C. The other part is called the Ricci tensor scalar. The wave tensor describes deformations of space-time. For example, gravitational waves, they expand in one direction and then the other and go on like this. So tidal deformations. It doesn't touch the overall volume. It just does this kind of deformations of space-time. Whereas the Ricci tensor, that touches the volume. So how much does something shrink or expand? So we can have a look at that close to the singularity. What happens? Then we will see that in a Schwarzschild black hole, it's only this wave tensor that contributes to this scalar that diverges at r equals 0. So only the deformation, and that makes sense because it was stretching out in one direction and contracting in other directions. So it's a deformation. Whereas in the universe, in our Rosen-Walker metric, that doesn't have any wave tensor component. It only has contribution from this volume components, the Ricci tensor scale, which are proportional to energy density. So as the energy density blows up in the past, we have a curvature singularity where it comes from this Ricci part. And there's an argument that's very, very important here, made by Penrose, this article, in another occasion, is that you actually suppose you start with a singularity. Then that's determined completely by this Ricci tensor. But then you have collapsing objects in the universe, and they evolve into these wave tensor singularities. So could it be that this wave tensor encapsulates the entropy? Why was the wave tensor 0, this kind of deformations 0 in the early universe, and then evolve into singularities? So in a sense, that's a measure of gravitational entropy, its conjecture. And the main point here is that these two singularities are very, very different from each other. The singularity of the universe and the singularity in the black hole. So once again, I would say the singularity structure shows us that we can't really map the universe onto the interior of a black hole. But what about a white hole? It has a singularity in the past instead of the future. Couldn't that be a black hole? Or be a universe? So once again, we have the horizons here surrounding a white hole. Same relationship. A singularity in the past instead of the future. And then light rays waited here very early on, and then everything has to exit this horizon. But this can't really be a universe either, because in this case, you would have the opposite behavior of the expansion and contraction. You would have the radial direction contracting and the angular directions expanding. You would also have the opposite singularity structure. And it's also known that white holes are very unstable objects. So you add some perturbation around them, and they can recollapse into black holes. This is described in a new book that just came very recently, which is actually very good. I just finished it yesterday. So white hole is not a good candidate either for our universe. So if we take stock of everything here, we can look at the horizon. It's absolutely much more than a black hole, but it's relative in the universe. The singularity in a black hole lies in the future, described by this wave curvature, but lies in the past and described by this Ricci curvature in the universe. The vacuum solution, a black hole is a vacuum solution. There's no matter there. It could be in a collapsing astrophysical system, you have matter and eventually becomes something in the end. But as a generic Schwarzschild solution, is a vacuum solution. The universe approaches a vacuum solution in the form of dark energy, cosmological constant, maybe, if you want to call that a vacuum solution. But right now, it's not a vacuum for sure. Isotropic? No, the interior is not isotropic for a black hole, but it is for the universe. But both are homogenic, so looking the same everywhere. So it can be different in different. Isotropic means that, for example, the expansion goes, increases in one direction, collapses in the other, and it does like that everywhere in the same way inside the black hole. So in that sense, it's homogeneous. So looking at this plot, I would say the universe is probably not a black hole. That's my argument. That's my statement. I stand by it. But could the universe create, or could black holes create new universes? There are many papers about this. There's a famous one by top-level Russian scientists, like McConnell did most of the inflation CMB calculations from '88. There's another one from 2021, 2 years ago. It's quite funny, but they have the same title after this question mark. And Brandenberger here actually worked also with these people later on, so there's a connection. But there are many papers actually claiming that when you have gravitational collapse, you can create a new universe. So we don't really know exactly what happens as we squeeze matter to a denser and denser region. So maybe something interesting happens. So let's look at the argument. There are two assumptions here. The most important assumption is an upper limit on curvature. That's the Kretschmann scale we saw before. As space-time curvature increases in gravitational collapse, it can't do so indefinitely. So you put some upper limit on that. The idea is that some kind of quantum gravity theory would describe actually how that limit comes about. You have a second assumption. Here they did this assumption just for the calculation, but it can also proven to be a dynamical effect. The Ricci tensor becomes proportional to a cosmological constant. So you have some kind of change in structural space-time as you reach this upper limit on the curvature. If you do that, so here is this plot again, or conformal diagram. A universe here where we are living, a black hole, two horizons, some other universe. This isn't super important, this is about white holes and other universe. This part is important, and the singularity here. Because what they claim is that you can easily replace that singularity with a new universe. So this singularity, we said it was a point in time in the future. So why can't you just transform it as a starting point for a new universe? And you can show that that's a perfectly mathematical, consistent way. You can even show that that could be created out of a dynamical evolution of a collapsing system. This new universe is a de Sitter universe. So this kind of contraction that we talked about that happens close to the singularity actually changes and becomes first a de Sitter contraction and then a de Sitter expansion. And the author writes that it may be possible to travel from our universe into a new one, which is the absolute future with respect to us. So we would live here somewhere on the outside, we will go into the black hole, and then we will exit into this new universe. So, clear prediction. How do we test this? It's really easy. So several models predict that new universes are created in the last stages of gravitational collapse. Also from string theory and others. So all you have to do is you go to Sagittarius A star and you see what happens inside. Testable, easy. And if you go at this velocity of the speed of light, it only takes 13 years in proper time. because of time dilation. If you even go faster, it could be like 2 or 3 years. That's like a postdoc time. But of course, we can't communicate it. But I find it very fascinating to think about this idea that the black hole at the center of the Milky Way could be maybe like a new universe was created. If you don't believe it, then please tell me what the end state of gravitational collapse is. This could also mean that our universe came from a black hole. Using the same idea, this is a paper by Eason and Brandenberger, is that you have some other universe described. First, you have the outside of a black hole, the formation of the black hole, and then you replace, it's the same argument, you replace that kind of singularity with the starting point of a distinct universe. And the author of this paper, they claim that you could actually use that even to solve some of the well-known problems like flatness, horizon problem, Hawking radiations, could be seed or structure formations. It's an idea, and there are models for it. A much more out there model is this idea by this morning from 1994, that actually every time in the universe where you create a black hole, you create a new universe. And inside these universes, in this high energy regime of gravitational collapse, you kind of go up into some more high energy parameter space and you fall down into some low energy world like the one we live in. But the parameters of your standard model change a little bit at each time. You inherit your parent universe's parameters of the standard model, but with a small change. And he argues that almost every small change in the parameters of the standard model with cosmology will either result in a universe that has less black holes than our present universe or leaves that number unchanged. So kind of our universe locally in the parameter space of the standard model, it maximizes the creation of black holes. This is what they introduce as an alternative to the anthropic principle. And it gives concrete predictions such as an upper mass of 1.6 solar masses for neutron stars and single field inflation. Now this has been broken. We have observed 2.3 solar masses for neutron stars, whereas the Planck data is very consistent with a single field inflation. But predictions come out of this. So it's time to wrap up. What are the conclusions? My feeling is that the universe is most likely not a black hole since the horizon singularity structure is so different. Event horizons can arise both during gravitational expansion and contraction. This shows that event horizons are a more general concept than just what you have for black holes. It can arise in two kind of gravitational scenarios. I think that's the important take on the message. You can even have a horizon in flat space-time if you have an observer accelerating at a constant rate. That also creates a horizon. So horizons are more generic than black holes. New universes will form inside black holes in the sense that there are models predicting this. And there are models in which our universe has been spawned from a black hole. So I think this part is super interesting. That new universes can be created inside black holes. And I think that's really, you can make a case there. Conclude, summarize everything in one sentence. I would say our universe is not a black hole, but a black hole is another universe. That's for me the message. Thanks.